To finish up some of these lectures on neural nets, what I wanted to do is walk through two specific examples of training neural networks. This is going to serve two purposes. First, I want to show you the code base. I want to show you the kind of work and effort and structure you're going to have to work with in order to actually write neural network codes and train them. So one of your best resources available to you is there are many resources now like ChatGPT, Claude, other, LLM type models, which allow you to even query and get code base out, which is, you can ask for little code blocks and it will come up with prototypes in almost any language you want. And so this is a really helpful way to start thinking about programming, because a lot of what it's doing is kind of sifting through GitHub and Stack Overflow to pull code in, and much of it is very useful. But I want to show you the code base and how you structure these neural networks and how you train them. The Jupyter notebooks and Python code is available for all these examples, so you'll have access to those. But I wanted to walk through the infrastructure and talk about how we go about programming these things. And I'm going to give you two very different examples. One is we're going to return back to the basic curve fit that we started with, which is fit a little oscillatory line. And second, and so that's a direct curve fit. The second one is going to basically learn how to build a time stepper. In other words, a sequence model. So I give you data and you're going to map from time t to t+1. So these are going to be the two models, but we're going to first start with the curve fit. Okay, this is all about machine learning. Now we're going to leverage the power of neural networks in order for us to sort of give ourselves a really rich infrastructure for advancing simulations or data in general. So first of all, I want to highlight one thing. There are a lot of neural network architectures out there. I'm going to just focus on feed-forward neural networks right now, which are kind of, in some sense, the very simplest of all neural networks. But I give you a sort of a chart here of all the kinds of neural networks that are available to you. And this is actually already old. There's a lot of new ones, especially things like transformers and UNets, in addition to go with all of these neural networks infrastructures. And so you see, one of the big choices you make right up front when you're deciding to do deep learning is, what architecture are you going after? In other words, what's your objective? What kind of problem are you trying to solve? And often, these neural networks are structured to solve certain types of problems, okay? And so you've got to get a handle on that a little bit in order for you to have the most success. You have to have sort of, in some sense, some idea of the varieties of things that might be out there. So for instance, here, RNNs, LSTMs, this first set of models is all about training sequence data in time. So going from t to t+1, t+2, t+3. Sequential data in time, especially temporal data, this is what the LSTM was built for. It's a really nice architecture for doing it. Whereas the AE, or the autoencoder, is all about looking for low-rank features in data. So instead of applying something like PCA, what you're looking at here is a way to go to a reduced order representation, reduced dimensionality, through a nonlinear function, which is the autoencoder, and then you can come back. So anyway, those are just two to highlight, but there's all kinds of architectures available today for you to use. And so, and it's evolving quickly. So this is just what's here, but like, we don't know exactly what's going to be available in a year, 2 years, 5 years. People are coming up with really innovative structures all the time. It's a very fast-moving field. And so part of it is reading papers, being aware of what people are doing in the community. And by the way, some of the ones that seem to work really well for something where everybody wants to try it, like transformers, it doesn't guarantee that it's going to be the best model for, let's say, sequence model for a dynamical system, right? You have to really think carefully and evaluate carefully things. Don't just go with, oh, everybody's using this kind of architecture, it must be the best. That's actually probably untrue, okay? But I just wanted to highlight this. There's a lot of variability. I'm just going to show you how to write feed-forward neural networks in these couple examples that we have today. All right, so let's go into some code. So I'm going to be very explicit about writing code here, and I'm going to show you the Python blocks. Again, The notebook for this is available to you, and so you can download that and start running code directly on it, or run it on your laptop and start directly starting to play around with the code and tuning the parameters, doing all the kind of things that you might want to do for this. So here's going to be the objective in this first one. And by the way, I introduced this example very early on in the set of lectures on neural networks, which is, here's the data. It's basically, this is the simplest example you could do. It's A cosine bx plus cx plus d. So the blue line is the perfect data. What I added to it was some noise. So that's what you see there, you know, this wiggly. So I added noise. That's your data. And your job is to be able to feed forward a neural network that models that data. And I'm going to do it in two scenarios. One in which I give you the data here in this black region, and I'm going to ask you how well do you do on either side of this region. Or the other one, which is I give you the data in the black region here, how well do you do in this region here, what I left out, which is sort of in an interpolation region, right? It's between data, where here I'm truly extrapolating outside of my regime, okay? And it turns out the performance of those two scenarios is drastically different. Because when you give me data training here and I have you walk outside, you really are doing extrapolation, and the neural network generically is going to fail or not do that well. So that's kind of one of the things that you're going to see right away with neural networks is, you know, when you look at the data, you could, you know, with your mind's eye, you're like, well, just fit an oscillation. The neural network seems to never learn the oscillation unless you do a lot of extra work. I've not gotten into work, but maybe somebody can. So there we go. But I did just some basic feed-forward neural networks. And these feed-forward neural networks, no matter what I did, I could never get them to oscillate outside of the region where the training data was. So in the tests region, they could never oscillate. All right, so let's start off with coding. So we're going to get right to it. We're going to go through these code blocks, and this is all in the notebook. But I just wanted to walk through sort of the infrastructure and the main code blocks to sort of get you a fast start of understanding what we're trying to do with this. So obviously you import numpy is np. I bring in scipy, matplotlib, and matplotlib. So here's the plotting algorithms. And now I bring in the torch utility. So I'm going to use PyTorch. You can pip install it, pip install PyTorch. Boom, you got PyTorch on your computer. And it directly interacts within your Python framework. So here we go from torch utilities. I'm going to import data loader. So what we got to do is when we bring in our data as an NP array, we've got to turn it into a torch object, okay? So we're going to import torch itself, and from scikit-learn some other functionalities that we'll be using as we go along. So these are just all sort of the preambles of imports that we want to bring in. Most importantly is right here, bringing in the torch utilities, okay? And again, all you have to do, go online, you can go look at PyTorch and just, you can either conda install or pip install that right onto your computer. It's very quick. And then now you have all of these machine learning tools or these neural network tools directly on your laptop, which are super easy to use, okay? So that's preamble. Now let's start off with what we're actually going to do. Let's make our data. That's what this next step is. And you can see this is just such a simple curve. But also, what I like about this example, it highlights so much of both the power of a neural network and the failure of a neural network on a very simple example where you can see the results, okay? So I'm just going to make a curve here. So I do an NP array, range from 0 to 50, steps of 0.01. So basically it's going to give me a bunch of points between 0 and 50 and steps of 0.01. So I have a large vector. I pick parameters for what is going to be my curve fit, which is right here. A cosine bx plus cx plus d. And I just pick parameters. A is 11, b is pi over 4, c is 1.5, d is 22. I made those up. I put them in there. That's the curve. So this is my, let's say call it my truth data. This is the curve I'd actually love to get back from my curve fit. But I'm not going to give you that data. I'm going to first add noise to it to make it a little harder for us. So I go and find the length of this vector, okay? And then I say noise is equal np random. So I make a random vector of size n, and then I add it to this. So my y noise is y plus 2 times noise. So the factor of 2 here just allows me to make the noise bigger or smaller. So this is the data I'm going to give you. I'm going to give you noisy data. And the reason I give you noisy data is kind of obvious, right? That you're never going to get perfect data. You're always going to get noisy data in practice. So I want to give you noisy data right up front here in order for you to use and start understanding how well does the machine learning model work, even under sort of those kind of circumstances. So this is all the data generation portion. And you might say this is too easy, right? Like, you know, really just a simple curve like this. And that's kind of a true statement. But remember, all I'm trying to illustrate with this example is just how does the neural network work for such an easy example, because you can really you can see what it does. You can actually see the results very clearly and understand both the strength of the neural network and some of the things where it's going to fail, okay? So that's the data generation portion. All right, so now let's go and start making training data and test data. Okay, and so what we're going to do with all that data, remember it goes from 0 to 50, is we're going to pull out a block of it. There's 5,000 points in there. And so what I'm going to do here is, first of all, I'm going to scale the data. This is actually a super important step in practice. And you'll see this in all kinds of codes when you download clones people's GitHub pages when they're working with code. Scaling the data is really, really important. So what we're going to do is put it through this min-max scaler. We're going to take all the data and throw it in there right here. Okay, so we're going to bring in min-max scaler. We're going to pull out data here, x1. Notice it's from 2,000 to 4,000. So I have 5,000 data points. I'm going to take from the 2,000th point to the 4,000th point, pull that out. That is going to be my training data. Okay, so those are the x values. These are the y values. So that's going to be the data I pull out that I'm going to use to do my training on. And once I've trained it there, I'm going to ask, how does it do outside of that? Okay, so I'm going to try to extrapolate outside of this. Of course, I could do the opposite example where I take the data on either side and interpolate, but this one's a little bit more interesting just for us to see how well does a neural network extrapolate. The answer is not very well. So you should keep that in mind. Okay, now I'm going to use the scalar. So here we go. XT, SC, which is the scalar step, fit, transform, I put the XT in there. In other words, I scale the X data, and here I scale the Y data. So I've scaled all the data for Torch, and this is an important step, really important to do. And then what I do is I turn them into tensor objects right here. Right here is where you take XT, you turn it Torch tensor, and then a Torch tensor. So now what you're doing, you're taking it from an MP array, which is what Python wants to work with, and to do NumPy type mathematics, and you've turned it into tensor objects that are ready to go into Torch and to be able to train on data. Okay? All right, so there we go. So this code block was all about scaling, pulling out a training data set, and setting up as Torch objects. You have to do all these things. Now, again, the only thing that you might change here is you can play around with what you're putting in as your training data set. Okay? All right, now we get to the heart of it, neural network. So now we're going to make a feed-forward neural network, okay? And this is a class here. You see it here, class FNN, so a feed-forward neural network. And I have to get to my computer so I can actually see this because it's too far away for me to see. And so the way you define this is right here, define init self. You're going to bring in some parameters, the input size of this, the number, the hidden size, the output size. So you're going to specify all this in your code. And specifically, you're going to specify how many layers you have, how big they are. All these things are going to be specified in here. And for here, if you, oh, wait a minute. There we go. That's it, okay. So layer 1, for instance, it's a Torch layer of the input size, hidden size, and that goes to layer 2 from hidden size to hidden size, hidden size. I can make these all different sizes, but what I've done here is the input size is, for instance, whatever the size of that input is, right? So I'm coming in, I'm going from X to Y, so I'm coming in with, and then I'm going to go into how many layers, how many how many nodes at each layer. That's the hidden size. And at the very end, I go out to the output size. Layer 4, hidden size to output size. So this basically allows you to control the size of the neural networks, how many layers. Here are the layers. There's 4 layers in this kind of architecture that you have. And then you can define the kind of activation functions you want. Check it out. So ALU, which is given by here, ReLU. So ReLU is rectified linear units, right? And so this is, or exponential linear units. Those are the 2 that you would have available for you. And so that's the first piece of this. The second is to define the forward pass here, which is, notice what it does, layer 1, and then ALU to layer 2, ALU, layer 3, ALU, layer 4. Okay, so you actually specify exactly what the activation functions are from one layer to the next. And this is exactly the structure of how you would do this. So by playing around with this, you see that you have full abilities to specify everything: activation functions, sizes, number of layers. And already you start to see the problems that you might have in training neural networks. How many layers should I have? What should be the activation functions? How big should those layers be? Should they all be the same? Should they be different sizes? How do you know? You hyperparameter tune. And that's, you know, that's one of the truths and the realities you're going to have to face when you train neural networks, okay? So I'm going to show you the example that we built here, but this is sort of what we're doing here overall. All right. We come here. Let's go to here. So now, actually, I'm going to go back one layer. I also changed this around to a more customized neural network, which is here. And this custom layer here, I want to show you this, is we take the same architecture we had previously, but now we sort of generalize it a bit here and allowed a little bit more flexibility for you to build a custom feed-forward neural network. So again, this architecture is very similar. It's got 2 blocks, the forward piece and the self-init, and it gives you all the specifications of the parameters you want to bring into it. You can specify the number of layers, activation functions, and how you want to set up the infrastructure here. And here, you can just specify generically, I want K layers, and this thing here will build K layers. Before, we built a 4-layer neural network, but now this allows you customization in the sense that it allows you flexibility to sort of say manipulate sizes and layers and activation functions much more easily with this customizable feed-forward neural network. Okay, so I'll kind of let you read through that, but this is all, again, in the code blocks for you to take a look at. And this is the kind of thing that you're doing. So remember when I showed a picture of all these architectures available to you for neural networks? Well, here's where you start. I mean, this is a feed-forward neural network, but for any of those architectures you'd pick, you'd be doing the same kind of things. You'd say, like, let's build the infrastructure. This is the infrastructure of that neural network. You get to specify things, and already you can say, you know, how should I pick all these things, right? I mean, this is part of what it means to do deep learning, is you're going to have to, like, do a lot of hyperparameter tuning. In general, people often will say, well, you know, yeah, I could have, you know, you try to make the layer. Here's a general rule. You might say, like, okay, if I get this thing working, can I make the layers smaller? Can I have less layers? So in other words, you make it as small as possible that you still don't lose any performance. Oftentimes that's what people do in practice, right? And so that just means you have to hyperparameter tune, like what happens if I have 40 hidden states versus 80? Oh, 80 works great, 40 not so well, 60 works as good as 80. Maybe that's where I cut it off because I start losing performance. And again, you see how many times you're going to have to train this to see which one works best for you. But that's inherent in this whole neural network endeavor. The minute you commit to training a neural network, you're going to be in this space where you're going to be doing a lot of hyperparameter tuning. You're very lucky if you could just pick default settings and it works. That doesn't happen very often. So if it ever happens to you, go get a beer. Call yourself lucky. Okay. All right. Now, once we have that, I've specified that. Then you just put it in here. Here's the model. Custom feed-forward neural network calls that in, and you bring in all the parameters you want. Remember, this is the input layer. This is the hidden layer size. So I'm going to go from 1 to 30. I'm going to have 30 and back down to 1. And I believe here it's 3 layers, and my activation is LU. So right away, I've encoded everything I want, mostly in here, right? So I could change this out to ReLU, ALU. It could make even more radial basic functions. There's all kinds of options here. I just picked 2 of them in there in that custom neural network. I could pick 10 layers, 2 layers, 5. And actually, the way I picked this 30 and 3, which are the 2 things I actually did play with a bit here, is that so it worked. Okay, so I hyperparameter tuned as well. So the notebook you have available to you reflects that some work was done to make that thing work out. And then once you've specified the model, you go here to train loader, data loader, train data set, batch size, check it out, batch size 64. So now you're starting your sort of stochastic gradient descent. Remember, the data I have was from point 2000 to 4000, so I have 2000 data points. The batch size is 64, so after it's walked through all the data, that's 1 epoch, okay, in the training cycle. All right, so that sets everything up with the data loader, the model itself. Some other things I want to do here is my learning rate. I get to pick that. Remember, the learning rate is how big a step do I take in the gradient descent? Number of epochs, how long am I going to let this thing train? Okay, you don't want to train it too short, too long. Often there's a thing called early stopping. You don't want to train it so long. Once you kind of get to an error floor, you definitely want to cut it off. Here's the optimizer, torch optimizer. Here we go. I can put in the learning rate and the model. And I'm training on MSE loss, mean square error loss. And then I start the loop to go train this thing. So that's it. Here, by the way, here's the optimizers, 0 grad. And I train the model, and it's just going to start training. Okay. That's the infrastructure for running this code. So you see, right away, this very simple thing that I've done, which is to say, I just want to do a curve fit on this simple oscillating curve, right? Which is parameterized by 4 parameters. Let's talk about how many hyperparameters I've already given you. Right here, learning rate is 1. I get to pick the optimizer, that's another. Let's leave the epochs off because it's not really a hyperparameter. I'm just going to start training. I'm going to watch how the error decays, and if it still looks like it's going downhill, I might take more epochs. But I also give you how many layers, size of the layers, right? So already a lot of things that you're going to have to hyperparameter tune. Now, what's in here currently is something that kind of works. In other words, when I train this thing, the error goes way down. I have enough layers. They're big enough. I got the right learning rate, so everything seems to converge quite nicely in the Jupyter Notebook. And by the way, that took me a while to do. This is such a simple model, but it took a while to get those, roughly in the right ballpark to get a good result. So again, all this is reflecting for you is the fact that you're going to have to work every single time you train this at your hyperparameter tuning. Okay? And then let's look at the results. And I've already shown this, but here is the interpolation results and the extrapolation results. So let's talk about the interpolation results. What I mean by interpolation. The gray regions is where I give you training data, here and here. And then I ask the question, how well can you predict what happens between them? Of course, the truth is right here. It's still oscillating, but this neural network, in fact, I can train thousands of neural networks, and pretty much it does exactly the same thing. They all draw a line between these 2 points. In other words, in a little surprising move, all it sees are oscillations, yet it can't figure out to do an oscillation here. Okay? Good enough. It's just doing the best job possible. It only has error metrics in here and error metrics there to fit that. You're not telling it to oscillate here. You're just saying, okay, this is a region I have no data. And it just says, okay, in that region, just walk across. In other words, fundamentally, it never learns anything like an oscillation, which is kind of an interesting thing that you can represent here. The error is still not that bad, right? That curve is almost like a line fit a little bit through the data. So, it's not that far off. But let's go over to here. This is the more interesting case where I'm extrapolating. In other words, all the training data, and I showed this example in the code, is right here. So this is the code. The training data is that gray region. So I train the model, and by the way, the fit in that gray region is exceptionally good. I can drive the error way, way down. So it's almost dead on to the data. And remember, it's trained on noisy data. And yet it gives me a super clean curve matching the truth, okay? And then I ask the question, is what happens outside of that training data? And I'm giving you 3 different models here. So here's one of the models, and each model is just simply, I just reran the code. Start with new random values for the weights, find me a solution. And of course, the error is almost close to 0, and I ask what happens out here. Oh, this model here, the yellow one, is way off. Not so bad on that side. Whereas the magenta one is not so bad here, goes off up here in general. So you can see what it does outside of its training data can be really massively different. And this is super important because when you have a neural network try to extrapolate, this simple example shows you it can be a problem, okay? And in fact, if I train 1,000 models on that extrapolatory setting, I've already shown this picture. Here's the distribution of errors. So some of the neural networks can get the error down to still not that small. It never learns how to oscillate, for sure. So it's learning on oscillatory data. As soon as you're outside of there, never oscillates, okay? So it's not like it's learned something fundamental like, oh, this is an oscillation. Certainly it never does that. Not with at least this feed-forward neural network with the activation functions I have. So the minimum error is here, but look at the distribution of error. There's almost an order of magnitude difference between a bad model that you might get out and a good model, with the average being, double what the error is or almost double or triple of what a good model is. And this is really important because you may be tempted to train this and train it and train it and say, look, here's how my model does. But you're actually using then this model to tune towards one withheld data set. And it's super problematic when you do that. This is the more accurate picture of what your model is doing in the extrapolation regime. Now, in this case, we knew what the truth was in the extrapolation regime, right? So we could actually look at it. And so one way to say it is you could bias your neural network to know what you know the truth to be. But the fact of the matter is, in many applications, you don't know what the truth is in the extrapolation regime. And it could be that your model is this one. So this is highly problematic in many ways. And it's just simply a reflection of when you try to do extrapolation. You have to be really careful. In the interpolated setting, right, it just simply draws a line. It's never that bad. It's not that good. But it's not like it goes way off. This can go way off when you're really extrapolating. And that is, I hope, a lesson to be learned on the simplest model possible, which is just simply trying to do a curve fit with a neural network. And so I like this example because it illustrates so many of the key features you got to be thinking about when you train neural networks.